So this proof illustrates the use of our new quantifier rules. In particular, it illustrates the use of universal elimination and existential elimination. We start with one premise. The premise is that every object is such that if it is A, then it is not B. And what we want to prove is that there's no object which is both A and B. Now, how can we prove that? Well, the backward planning suggests the following. Our main operator in the conclusion is the negation sign. So I'm going to try to prove this using negation introduction. And negation introduction always requires the use of a subproof. So I'm starting with the assumption that there is an x such that ax and bx, and I want to infer a contradiction from this assumption. Since if I can infer this contradiction, then I can infer that it's not the case that some x is both a and b, and justify this inference by means of negation introduction. Okay, so that's my basic proof strategy and the basic proof setup. Now, let's move on and do a little bit of forward planning. So in line 2 of my proof, I have an existentially quantified sentence. And forward planning suggests that I should use existential elimination to infer something else, to infer my desired conclusion here. So existential elimination works like this. I start by making a new assumption. I'm going to assume that object B has properties A and properties B. So A, B, and BB. Here I've taken the embedded formula AX and BX in line 2 and replaced the variable X by means of the name B. And I'm going to try to infer bottom, since then existential elimination applied to lines 2 and the subproof is going to allow me to infer bottom down here. Okay, so in line 3 I have the assumption that A, B, and BB. I am going to go ahead and separate the two conjuncts here. So AB and BB. And both inferences can be justified by means of conjunction elimination applied to line 3. So now looking at line 1 of my proof, I see a universally quantified sentence. And this sentence allows me to infer that if B is A, then it's not the case that B is B. And I can justify this inference by means of universal elimination applied to line 1. And now I see a conditional in line 6 and the antecedent of that conditional in line 4. And so I can infer the consequent of this conditional by means of conditional elimination applied to lines 4 and 6. And now I can infer bottom, citing bottom introduction and lines 5 and 7. And I can infer bottom again, citing existential elimination and lines 2 and the subproof from 3 to 8. And now I can infer our final conclusion by citing negation introduction and the subproof from line 2 to 9. And that's our final proof. Here's a proof illustrating the use of existential introduction and universal introduction. We start with the assumption that no object is both A and B, and we want to prove that everything is such that if it is A, then it is not B. Now I see that this is a universally quantified sentence, And backward planning suggests that I should try to prove this by means of universal introduction. And in order to do that, I need a sentence of the form, if AB, then not BB. Since if I have a sentence of this form, then I can infer my universally quantified sentence using universal introduction. Now, the main connective of this sentence here is the conditional. And so I'm going to try to prove this by means of conditional introduction. And I start with the assumption that AB, and I want to prove that not BB. Since then I can infer that if AB, then not BB, citing conditional introduction and the subproof from line 2 to somewhere else. Okay, so now my next target is I want to prove that not BB. The main connective here is the negation sign. So I'm trying to prove this by means of negation introduction. And I start with the assumption that BB, and I want to derive a contradiction, since then I can infer that not BB, citing negation introduction and the subproof from line 3 to somewhere else. Well, now I have AB and BB, and I can conjoin these by means of conjunction introduction, AB and BB. Conjunction introduction applied to lines 2 and 3. And now I can use existential introduction to infer that there is an X such that AX and BX. Citing existential introduction applied to line 4. And now I can infer bottom, since we have the sentence there is an X such that AX and BX and its negation. So bottom introduction applied to lines 1 and 5. And now I can justify my negated sentence here, not BB, by citing negation introduction and the subproof from 3 to 6. And I can infer the conditional here in line 8 by citing conditional introduction and the subproof from line 2 to 7. And now I can infer our final sentence here by citing universal introduction and line 8. So that's the final proof illustrating the use of existential introduction and universal introduction.